Deep inside our power grids, there are these massive, spinning giants, hydro generators. They're really the heart of our clean energy infrastructure. But what if these machines are constantly talking, sending out these tiny signals about their health? Well, today we're going to learn how to listen to them.
I mean, just try to picture the sheer scale of these things. They are running constantly, day in and day out, giving us that steady, reliable power we all just expect to be there. They're pretty much the bedrock of stability for our entire electrical grid, the real unsung heroes working away in the dark. And believe me, when one of these giants fails, it is not a quiet event. We're talking about a sudden, catastrophic shutdown, one that can spark cascading problems, cost millions, and seriously jeopardize the power supply for entire regions. And this, right here, is the crucial question. What if we could actually hear those earliest, faintest signs of trouble? What if we could translate those little whispers into clear, actionable warnings, giving us time to act before a disaster strikes? That's exactly what we're going to dive into today. Okay, so to really get the solution, we've got to first appreciate the problem. Let's take a look at why these incredible machines fail and what the real-world consequences are when we're just not listening. Now, check out this data. This comes from a huge industry survey by CIGRE. That's the International Council on Large Electric Systems. And it's pretty eye-opening. A full 50%, half, of all unexpected shutdowns are caused by one single thing, the breakdown of stator winding insulation. It is without a doubt the #1 vulnerability in these massive machines. And the price tag for that kind of failure? It's just staggering. We're not talking about a simple repair bill here. We're talking over $10 million for a single emergency event, especially once you factor in all the lost revenue and the absolute chaos of an unplanned outage. That is a massive, and as we're about to see, a largely preventable expense.
So how have we traditionally tried to stop this from happening? Well, the old way of doing things was basically a shot in the dark. It was a high-stakes gamble with our most critical infrastructure.
For decades, maintenance was all done on a fixed schedule. After a certain number of hours or years, you shut the machine down and take a look. But that's the gamble. You might be spending a fortune to fix a machine that's actually in perfect shape. Or worse, a critical fault could pop up the day after a scheduled checkup, leading to a surprise failure anyway. It's just not efficient. This is where the whole philosophy just flips on its head. Instead of forcing our schedule onto the machine, we start letting the machine's actual condition set the schedule. We stop guessing and start listening. It's called condition-based maintenance, or CBM, and the logic behind it is just beautifully simple. You only do maintenance when the monitoring system tells you a problem might be on the horizon. It's like having a real intelligent conversation with the equipment, moving us from asking what if to actually knowing what is. Of course, for any of this to work, you have to be able to trust the system completely. And that trust really stands on 3 critical pillars. First, the monitors have to be good at detecting the most common ways these things fail. Second, false alarms have to be incredibly rare. You can't be chasing ghosts all the time. And finally, the system itself just has to be tough and affordable. Okay, let's get into the really cool part now, the tech. How do we actually listen to these machines? How in the world do we pick up those faint whispers of failure from deep inside a massive, noisy spinning generator?
So remember that #1 cause of failure we talked about? That stator insulation breakdown? Well, it doesn't just happen all at once. It starts with something called partial discharges, or PD for short. Just think of them as tiny, microscopic electrical sparks happening deep inside the insulation as it gets older and weaker. These are the very first whispers of a developing problem. But how do you hear a tiny spark in what is basically an electrical thunderstorm? The solution is just brilliant. It's called the time-of-flight method. The system uses a pair of sensors. Now, all that harmless background noise hits both sensors at the exact same time, so the system just tunes it out. But a real spark from inside the machine will hit the closer sensor just nanoseconds earlier. That tiny, tiny time difference is the whole secret. It's the signal that flags a real internal warning. And partial discharge, well, it's just one piece of the puzzle. You can see here we can do a full health check. We can monitor for stuff like excessive end-winding vibration. That could mean a support structure is loose. Or we can detect uneven magnetic flux, which points to shorts in the rotor. We can even watch for high shaft voltage. Each symptom has its own specialized diagnostic tool.
Look, the last thing you want is a dozen different systems that don't talk to each other. That's where an integrated platform comes in. It acts like a central hub, pulling all the data from all these different monitors into one single unified dashboard. This gives operators a complete, holistic picture of the machine's health, all in one place, and they can access it from anywhere.
So what's the big payoff here? What's the end game? It's all about moving from a reactive break-fix world to a proactive one, a world of prediction and prevention. Let's look at the real-world results of this new philosophy.
This quote from the source material really just nails it. It's about being in control. Instead of a chaotic, emergency shutdown on a holiday weekend, you find the problem months, maybe even years ahead of time, and you schedule the repair during a planned, low-demand period. It turns a potential crisis into just another routine task.
And the financial impact? It's just incredible. The data shows that the cost to fix a problem you catch early is often less than 1% of what it costs to do a full rewind after a catastrophic failure. This isn't just a small improvement, it's a complete game changer for how these assets are managed.
So the bottom line is crystal clear. With a condition-based maintenance approach, generator availability goes way up because you have far fewer unplanned outages. Unexpected failures absolutely plummet. And as a result, your overall repair costs are drastically reduced. It's a win-win-win.
And this isn't just about one single power plant. Let's zoom out and think about the big picture. For all of us, this means more reliable clean energy. It means utilities can spend their maintenance budgets way more intelligently. It means our critical infrastructure lasts longer and our entire power grid becomes more stable and resilient. It's a fundamental shift in how we care for the very backbone of our modern society.
Which kind of leaves us with one final thought. We've just seen how applying this kind of smart monitoring can completely transform the reliability of our power grid. It really makes you wonder, what other complex systems, in industry, in infrastructure, maybe even in our own lives, are sending out these quiet warning signals, just waiting for us to finally find the right way to listen?